Hello, my name is Rob Reynolds. Welcome to Business Calculus, Chapter 2, Section 5. Today we're going to learn the chain rule. And the first thing you need to know about a chain rule is it's really just a function within a function, or when you see a function within a function, you're going to apply the chain rule. And this does not mean multiply. This is pronounced f of g at x. And when you see this notation, you'll probably want to write it like this because there's an inside function here, and we're going to do a little let u be that inside function or the g at x function. So we're going to be doing the chain rule. We're going to be reviewing the general power rule. And then remember, you always want to try to simplify before you start finding the derivative. That will greatly help you. So again, the chain rule is when you see a function within a function, we're going to do some let the inside function be u, and then this thing is called du, the derivative of u. So u prime is the derivative of u. So whenever you have a u, you're going to have the derivative of u as well. So starting right here, this is a function within a function, and they're going to ask you to find the derivative of that. And the derivative is literally the derivative of the outside, which is this g prime x, right down the inside. So they just took that h of x function and just wrote down the inside function. So it's the derivative of the outside, right down the inside. And then what's this? The derivative, or then times the derivative of the inside, which sometimes I refer to that as the du, the derivative of u. So again, it's the derivative of the outside, that's the g, just do the normal derivative, right down the inside times the derivative of the inside. Again, there's different notation for these, but that's the easiest way to kind of think about it. You may ask, what gives me the right to introduce a u in the problem? And that's because I'm just multiplying the top by du and the bottom by du, and of course they cancel, and I'm just left with that dy dx again. So oftentimes we'll call this a u sub, but remember, whenever you do a u sub, we have to remember du, the derivative of u. Sometimes I talk about these cows. If I'm trying to take the derivative of some cow to the nth power, well, you just do the power rule. You take this n, multiply by the 1, so it becomes derivative of the outside, right down the inside, don't forget to decrease the exponent by 1, times the derivative of the inside. Well, the derivative of this cow is that little baby cow, or sometimes I call it the baby calf. So, but that's the du. So I'm just kind of making fun here. Here's an example. 5 something cubed. So again, it's the derivative of the outside. That's how they got the 15. Write down the something. Don't forget to decrease the exponent by 1. And then the derivative of whatever that something is. In other words, that's that little baby cow, or that's the d. This whole thing is my du. And there it's worked out for you. So you can see there's all sorts of discussions. Here's the chain rule in a comic, and they talk about this little guy right here being du, the little penguin. So the mom is giving birth, and this little baby du, well, sometimes du is bigger than the mama, and you'll see a couple examples of that, I think. So again, this is what gives me the right to introduce the du. You can read through these slides posted on a Blackboard. There's probably more slides than you need, but for those people that aren't listening to the video, at least they can read. So just set this up. Don't find the derivative. Just tell me what is the inside function, or the g at x function. So looking at this guy, what's inside the fraction? Well, I would say x plus 1 is inside. It's in the denominator. It's inside the function. And so if you let that be the inside function, then the outside function, which is the y value, would just be 1 over whatever you replaced all of that with. And there's the something, 1 over u. And you let u be the inside function. So for part B, I would probably let, again, the inside function, let this guy right here, this is inside the radical. So I'd probably say let u equal, well, there it is right down here, let that be the inside function. And then the y with the outside function would just be the square root of u, which we will probably write as u to the 1/2 because it's a lot easier to take the derivative of u to the 1/2. So there's some answers to this. Again, I would probably encourage you to write that as u to the 1/2. Answers are posted on Blackboard. So again, what should we let u be here? 99.9% of the time it's going to be the inside function. There are exceptions. And you may say, well, how do you know if you're wrong? Well, if du's not in the original problem, you got to look for du. And what the heck is du? Well, it's the derivative of u. So let me show you. If we let u be that inside function, then du is what? 2x. So just remember 2x is going to be that little baby calf cow at the very end. So I'm going to follow this rule, the derivative of the outside, so 3 times 1 is just 3, so y prime 3, right down the inside, don't forget to decrease the exponent by 1, and then times that little baby du, and of course you can clean this up by multiplying this together. 6x, x squared plus 1 quantity squared, and in calculus we probably don't want to multiply that out because I like things in factored form, so just leave that as the final answer. Let's see if the author does the same thing. Yes, he does. So don't try to multiply that. In fact, you can't do this because before multiplication you got to take care of the exponent, but you don't want to distribute that exponent. This would be a huge mistake. Would I have to take off lots of points if you tried to distribute that 2 like that. You actually have to do the FOIL method. Square the first 2 times the product and then square the last. So that guy foiled is this, and then you'd have to multiply that by 6x. But again, don't do all that. Just leave things in factored form. Don't multiply them out. I know you're used to multiplying things out, but we're not going to multiply things out anymore. So remember, you may ask, Mr. Reynolds, why weren't you worried about du before? Well, I was. I just didn't want to confuse you with it. Look at this. Here it's the derivative of the outside, right down the inside, decrease the exponent by 1, times the derivative of the inside. Well, the derivative of x is dx, but it's with respect to x. So when I've been writing du, another way to write that du, see right here, du is 2x. Another way to write that, another notation for it, is du dx. It means the derivative of u with respect to x is 2x. I'm going to have an x in it. Another way to write it is just u prime is 2x. So there's all sorts of ways. I get lazy sometimes and just say du, the derivative of u, but really I should be writing du dx because it's telling you with what respect I'm taking the derivative for. So I've really been doing this all along. It's just this equals 1, and nobody ever writes dx because that just muddles up the problem, and we can simplify it real quick. So let's do another one. The derivative of the outside, right down the inside, times, don't forget to decrease the exponent, times the derivative of the inside. So the derivative of 3x minus 2x squared is 3 minus 4x. And that gets multiplied by this 3 out front. By the way, if I fill in this, I really let u be that inside function, which is what? 3x minus 2x squared. And then I found du by taking the derivative of this green, 3 minus 4x, and that's my du here. So I'd probably just leave this 3x minus 2x squared, but we can multiply probably this 3 times this guy just to clean it up a little bit. We don't need to multiply out because I like it in factored form, but don't leave 5 times 4. Probably write this as 9 minus 12x. No, I wouldn't. I don't know. Let's leave it. I keep saying factored form. Let's not even do 9 minus. Let's see what the author does. Hopefully they leave it in factored form. Yes, he does. Factored form. But I would certainly take 9 minus 12x times the quantity. 3x minus 2x squared. That's the same mathematical answer. It's just I prefer factored form. Of course, as we move along in these examples, they get a little harder and harder. So this one deals with a radical, and I just want to refresh your memory. Did you know that the square root of x is x to the 1/2? And the reason why is because there's a little invisible 1 there and a little invisible 2 that nobody writes, but they exist. They're there. So I see here the cube root of x squared. So did you know you could write that as x to the 2/3? I think that would really help us out. So I'm going to do a quick little rewrite. X to the 2/3. We'll ignore this just for a moment. I just got to find y prime, and then I can evaluate y prime at 2. So let's do the chain rule. The derivative of the outside, right down the inside. Now don't forget to decrease that exponent by 1. So 2/3 minus 3/3 is negative 1/3. We'll deal with that in a moment. Times the derivative of the inside. And the derivative of x squared plus 4 is 2x, which I would probably not leave this because you're going to say it's factored form. It's factored. Well, you'd probably multiply that up together. So how about those two yellow things multiplied together gives me what? 4x over, and well, there's a 3 in the denominator. And do you know this negative means throw that in the denominator as well. So you could raise it to the 1/3, but I would probably think it would look better if you just put this back into cube root form, because it was originally in a cube root. So let's just put, because instead of to the 1/3, that is cube root. So the cube root of x squared plus 4 is my best guess for y prime. So the goal now is to answer the question, and it says find out whenever x is 2. So y prime 2 means every time you see an x, plug in a 2. So 3 times the cube root of, let's just do it, 2 squared is 4 plus 4, and that means it's the cube root of 8. Did you know the cube root of 8 is 2? So 8/6, which reduces to 4/3. All right, so we found, did they say write the equation of the line? Yes, find the equation of the tangent line. Well, we just found the slope, because the slope is the derivative. Slope of the tangent line. So now we've got the y equals the slope, mx plus b. Most textbooks teach you to go to y minus y is equal to slope x minus x, but my calculus teacher told me just to go to y equals mx plus b, so that's what I've been used to. So we need an x and a y. Ooh. Unfortunately, we weren't given a y. We were given the x coordinate, but we don't know what y is. But you can find y by just plugging this 2 into the function. So let's just do that real quick. The cube root of 2 squared, which is 4 plus 4 squared. 4 plus 4 is 8. 8 squared is 64, and the cube root of 64 is 4. So I think I just found the point, 2 comma 4. So now I can use that for x and y. So if y is 4, x is 2. And, oh crap, I'll find common denominators. I've got 8/3 over here. I've got 12/3 over here. And I'll subtract off 8/3. So 12/3 take off 8/3 is a whopping y-intercept, which is 4/3. So now I've got the slope. Wow, that's interesting. The slope is the same as the y-intercept. So I would write it as 4/3 x plus 4/3. Here's, again, worked out solutions are posted on Blackboard. Yay, they got the same derivative. They got the same slope. And hopefully they got the same equation of the line. Looks pretty good. Example number 5. In the last section, we learned the quotient rule. And this mentions word quotient, but the hint says, let's not use low d high minus high d low all over low squared. Instead, let's just rewrite this before we try to take the, and look at this. This becomes really simple. If I bring that 2, this whole thing up top, it becomes a -2. So now I can do the chain rule. The derivative of the outside, write down the inside. Now, everyone always forgets to decrease the exponent by 1, but we don't want to do that. And then times the derivative of the inside. And the derivative of 4x minus 3 is just 4. So I would probably put this back in the denominator. Let's not leave negative exponents. So let's leave -40 multiplying. Again, let's just simplify. I mean, you're going to say that's factored. No, let's multiply that up and together. -40 over 4x minus 3 cubed is probably final solution. Let's see if the author, yay, agrees. So use some simplifying techniques before you start taking the derivative. One of the simplifying techniques throughout this whole thing that we're going to be emphasizing is factoring. So we're going to sit here and just review a factoring skill. And if you haven't done chapter 0, I think there's a couple factoring in that too. So factoring says pull out the GCF. So let's see, what can you divide both of these things by? And I think we can divide by 3, and it looks like x squareds are common as well. So that's called the GCF. So I'll pull out a 3x squared, and I'll start dividing. 12 divided by 3 is 4. X cubed divided by x, you subtract the exponents, plus 3y, and the x squareds are gone. So notice I pulled out the smaller of the exponents. So you're going to do the same thing for this guy. Which is smaller, x or x to the -2nd? and I think you would say negative numbers are smaller. So you're actually going to divide by x to the negative second here. Oh, let's grab the numbers. Is that a 2 that's common between 6 and 8? And then what's smaller between y to the negative third and y to the fifth? You guessed it, y to the negative third. Now that looks weird, but that's the concept. Always pull out the smaller exponents, and negative numbers are smaller. Why? Let's look what happens. This will be nice in here, I think. 6 divided by 2 is a 3. The x's are gone. What is y to the negative third over y to, well, that's gone too. So 3 plus 4, the x squared, here it goes. What's y to the, let me try this one more time. What's y to the fifth divided by y to the negative third? Well, you rewrite the base and subtract, and that's just y to the eighth. Isn't that nice? That's easy to find roots for, which we're going to be doing later. So that's why they want you to pull out some crappy negatives so that it won't leave crappy negatives inside the factor. So here comes example 6, where I think this is the first example we're going to be using the chain rule and the product rule, because I see a product here. The derivative of the first, right? Let's do it. The derivative of the first, right? Oh, I think, no. I think I taught in this class 1d2 plus 2d1, right? Let's do that. 1 d2. Oh, Lord. Well, I'm going to rewrite, before I take the derivative of this guy, can I write it like this to the 1/2? So I'm just going to take the derivative of this guy. So the derivative of that guy is the derivative of the outside, write down the inside, don't forget to decrease the x mark 1, times the derivative of the inside, and the derivative of the inside is negative 2x. So let's see, this is 1d2 plus, oh my gosh, here we go, 2, I'm going to write this as 1 minus x squared to the 1/2, and then d1 is 2x. So let's see if I can clean this up just a little, and then I'll try to simplify it by factoring. Oich. And what do I mean by clean up? This is 1/2, and the negative 2, I think clean up pretty good. Well, at least it clears up to a negative 1. And then I've got this x times this, x squared times x, which is, so can I just write this as a negative x cubed 1 minus x squared to the negative 1/2 plus 2x times the 1 minus x squared to the positive 1/2. And now we're back to the other lesson, which is smaller. Because this factor is really the same as this factor, just like I had done before. They just have different exponents, right? So they're kind of like both y terms. So these are both 1 minus x squared terms. I got to pull out this, and I think I can also pull out an x, because I think this term has an x and this term has an x. So let's pull out, you can pull out a negative x, but I'm just going to pull out an x. And I'm going to pull out a 1 minus x squared to the negative 1/2. And what do I mean by pull out? It literally means think about dividing each term by that GCF or whatever you pulled out. So I'm going to write that down here just so I don't lose track what I'm dividing out, the greatest common factor. So now I'm left with a negative x squared I think this will cancel all together. This will be plus 2 times this 1 minus x squared, and then I have to worry about subtracting. 1/2 minus a negative 1/2 is just to the first power. So this is negative x squared plus 2 minus 2x squareds, which is negative 3x squareds plus 2 times this x, and then this guy has a negative exponent, so instead of writing that thing in the numerator, which it is, I'll throw it in the denominator and make it back to a square root. Because x to the negative 1/2 equals 1 over x to the 1/2, which is 1 over the square root of x. So get used to simplifying in that fashion. Let's see if the author worked it out similarly. Yeah, looks pretty good. Good. Same answer. So in the last problem we did the product rule. This one we're going to try the quotient rule, which is low d high minus high d low. I don't think I can avoid it like I did in example number 5 where I could just throw the exponent up top. So I think I'm going to, oh, and I see chain rule. The derivative of the outside, write down the inside. See, I've got every time you have an inside function, so every time you have f at g at x, I've got a function within a function, and I can see the inside function is this 3x minus 1 divided by x squared plus 3. Don't forget to decrease the x1 up times the derivative. Here comes du. Here's an example where du is just huge, because all of this is du. That's the little baby cow, which is by no means a baby cow, because I have to do low. Sorry for my dog barking. This kid's playing out front. Low d high minus high d low all over low squared. So that's that little baby cow. Oh yeah. So this, I'll write it. 3x minus 1. Now I know how you guys feel doing homework. Oh, do I really have to write that out? So this times this becomes x squared plus 3 cubed, because you rewrite the base and add the exponents. Up top, I've got 2, I'm going to leave it, 2 times 3x minus 1, because that's in factored form. I'm going to try to clean this up just a little bit in here. This is 3x squared plus 9 minus the quantity of 6x squared minus 2x, but when I distribute this, it's really, 3x squared minus 6x squared for a negative 3x squared. This is, if I distribute this negative, going to be a plus 2x, and I keep the plus 9. And I don't think that factors more, so I think I would stop right there. And again, here's worked out solutions. The application is when you see rates change, all you do is find the derivative. You can look at that last problem for yourself. Again, go to Blackboard and check out worked out solutions. I hope you found this video helpful. If you have any questions, feel free to email me.